Attendees are in listen-only mode.
Hello everybody. We just let everybody connecting to this webinar, and we will start in 2 or 3 minutes. Thank you very much for your patience.
Hello, welcome everybody, and good morning, good afternoon, good evening, and welcome to the OPAL-RT Child Teaching Network webinar. I present myself. I'm Pierre Badar. I will be the lead demo today, and my presenters will be Pierre-François Allard, Sales and Marketing Director at OPAL-RT Technologies, and Ben Bach, Market Development Manager at National Instruments. If we go through the agenda of the webinar today, we'll start with a brief introduction to OPAL-RT Technologies and to National Instruments, and then to the collaboration between OPAL-RT and National Instruments. We'll then go to a short introduction to OPAL-RT Child Simulation and the OPAL-RT Child Teaching Network. Then I'll go through the live demos. We have 3 demos today. So first, with a boost converter. Second demo will be a boost converter with an external controller. And finally, a 3-level NPC converter. After that, I'll go through an explanation about AHS, which is the FPGA-based solver used in these demos. And we'll finish with a pair of questions, or approximately 15 minutes. So if you have any question, I invite you to use the question feature of the GoToWebinar panel. We've got a comment saying that the microphone quality seemed a bit bad, so I'll try to speak a bit louder. I will now pass the presentation to Pierre-François Allard, my colleague, who will explain you, who will give you explanation about who is OPAL-RT Technologies.
Hello everybody. Before we start the presentation of both OPAL-RT and National Instrument companies, there's a lot of questions that I would like to answer right now. What is the bound of our relationship, and what is the objective between this relationship and this partnership between National Instrument and OPAL-RT Technologies? Well, this is very simple. For many, many years, as you know, NI, National Instrument has been a leader in the most affordable, versatile, and innovative systems for test and measurement, especially hardware in the loop. And on our side, as you may know, some of you, we've been one of the leaders for the power electronics software on FPG. So we decided today to work together to provide an offer to the academic sector, to provide one of the best offers that combine the hardware of National Instruments with our power electronic FPGA software. So that's one of the main purposes of our collaboration. And now we'll continue by talking to you about the OPAL-RT technologies in brief. So for people who don't know us, we've been founded in 1997. Our headquarters is in Montreal, this nice building. We're more than 100 employees, and we have over 500 customers worldwide. We have two main expertise in hardware in the loop testing. The first one is power system, and the second one is power electronics. And with this expertise, we address many markets, such as aerospace to automotive, to research sector, to the academic. Without this, okay, the sound is bad. So if the sound is bad, I will change. Well, I think it's time for them to speak out. So on our side, we will do some improvement with our side.
Good morning, everyone. I'm Ben Black from National Instruments, Pierre François. Thank you for inviting me to take part this morning. At National Instruments, we think that working with OPAL-RT as thought leaders and technology leaders in the area of power electronics, hardware in the loop test is a great stepping stone and a great capability for our customers. Really, I think at the end of the day, this collaboration really will facilitate our customers and our end users to create better and more flexible and more cost-effective hardware in the loop test equipment. So National Instruments and I personally am quite excited about this collaboration. If you don't know much of National Instruments, let me give you a little bit of a background. National Instruments we think of ourselves as a tools provider for engineers and scientists. We want to accelerate productivity, innovation, and discovery in the areas of engineering and science. National Instruments as a company, we are headquartered in Austin, Texas. We're roughly a $1.2 billion company, and we operate in markets kind of across a broad range of different application spaces, from aerospace to power systems to automotive and to academic, obviously. We have a strong position in the academic space, and we want to facilitate the teaching and education of engineers and the next generation of engineers. So when it came time to talk about collaborating with OPAL-RT, it was a very logical first step for us to partner in the academic space, for us to be able to facilitate this power electronics, hardware in the loop collaboration specifically in the academic area. So we're excited about being able to launch our collaboration in this academic space. So with that, I will pass back to Pierre François for him to talk about what it is that we're collaborating and we're announcing today.
Thanks, Ben. Okay, so I hope the sound is better on our side. If there's anything, you could raise a question, and we'll try to do our best to provide you a top quality of sound. So today we will present you our Power Electronic HIL Teaching Laboratory. And this teaching laboratory has been created with the effort of National Instruments and OPAL-RT Technologies. So it's an educational courseware intended to teach power electronics to undergraduate students. So this Power HIL teaching laboratory includes software, hardware, and teaching exercises. So before going with the demo, we'll just give you a small overview of the component of this teaching laboratory. So first, in terms of software, when you get this Power HIL teaching, Power Electronic HIL teaching laboratory, you get the main interface is National Instrument LabVIEW. So Thierry will show you and do some demonstration about how the panels are made and how you could manage the experiment. Of course, underneath, even if you use OPAL-RT technology systems or National Instrument systems, OPAL-RT provides a specific solver into the FPGA called EHS from the FPGA SIM family by OPAL-RT Technologies. And the specific solver has been adapted to give a very accurate result on any power electronic schematics. And you will know a little bit more about this feature during this presentation. In terms of hardware, I just want to give you a brief introduction about how generally it's working. So basically, if you are not familiar with the concept, we have HIL, which stands for hardware in the loop, and RCP, which stands for rapid control prototyping. So one of the main ideas is that we want to provide also a feel to the students about what is the HIL and RCP experiment, because we know that in the industry this concept is well practiced and well known. So in terms of HIL, this is where we do the simulation of the plant. So as you could see, could be a boost, an inverter, a converter, and so on. And on the RCP side, this is where we will design the controller, or we could adjust the PI controller and so on. Okay? So in terms of hardware, you have the choice of two packages. The first one is you could use the OP45000 family from OPAL-RT Technologies. And the second one, you could use a compact Rio from the National Instrument. In terms of RCP, you could make your experiment using the OP8665 from OPAL-RT Technologies, or the famous Rio from National Instrument. Okay? I will let Ben continue, but what we will present you today is the first 4 modules that we've made for this specific package. So we're talking about a DC-DC converter, AC-DC rectifiers, a DC-AC converter, and a 3-phase, 3-level NPC converter. So without making you waiting, I will let Ben, who speaks way better English than me, continue with the laboratory exercise, just to give you a brief introduction about what we provide when we, in terms of laboratory, when we provide this package. Thank you. Let's go, Ben.
Yeah, so I think one of the incredible strengths of this software that's been produced by OPAL-RT is the courseware that comes with it. So when you download the toolkit, it has not only the exercises for the students to do and the software to run those exercises, but the PDFs for the courseware material to go along with it. And the courseware has been written in a way that the students could literally walk into a lab, you could hand this courseware to them, and they could go through the exercises kind of directly. It's a ready-to-go laboratory out of the box if you want to use it that way. So let me go through the courseware a little bit. This is a PDF from the course material, and if I scroll back up to the top, it starts off with the laboratory setup and kind of the background about the equipment being used in the system. Moves relatively quickly through the hardware and the software required. We get setup instructions and those sorts of things, and then moves into the objectives of each course. So there are 4 modules, as Pierre-François mentioned a second ago, and I'll talk about the 4 modules in a second. But each of the modules comes with an objective and has the technical background, the theory behind the different systems, going through the equations of the systems, the circuit diagrams, all of the technical details of the system, and then moves into the implementation of the system in the hardware in the loop and rapid control prototyping stages. So if I go through the courseware, I see I've gotten through the technical background, and I move into the exercises. And the exercises have well-defined objectives and well-defined goals for the students to go through, even to the point of having having question and responses kind of written there in the material. So as an instructor, I could literally walk in, hand this to my students, have them work through the examples, have them work through the exercises, fill in the appropriate places, and turn in this material at the end of the course for evaluation. It's an out-of-the-box, ready-to-go course for power electronics teaching if you want to use it in the out-of-the-box manner. So I'll go back to the PowerPoint now and talk about a little bit about the labs themselves. The first module is to discuss and to talk about DC to DC converters. So it'll go through boost, buck, and boost buck converters and look at all the characteristics of those circuits. The students by the end of it will be familiar with not just the theory but the implementation of those circuits in an open loop and in a closed loop fashion. And so to explain a little bit more about this and to show our first demo, I'm going to pass the baton back to Pierre-Yves to show us a demo of the courseware.
Thank you, Ben. So the first demo will be a boost converter. So I will just share my webcam so that you can see the actual setup. So now you should have the webcam image appearing in your screen. I invite you to increase its size by dragging its upper edge if you want to have more details on the webcam content. So as was explained before, here in this demo we have the compact Creo here that is running the power electronics simulation, and in this setup we have a Mario board next to it that will be running the external controllers for the demo that uses the external controller. So if I go to the presentation itself, I'll just share I'll go to the LabVIEW Project Explorer. Sorry. So here you have the LabVIEW Project Explorer. Actually, the model is already loaded. It's already running on the compact Creo. So if I open this VI, I will just deploy the simulation here. So now you see the boost converter already running. I disconnect the external controller. So this is the behavior of our boost converter. So it includes an IGBT, a diode, and an RC load. And the DC voltage here, you can see that it's set to 200 volts. The goal of the boost converter, as you probably know, is, as it's a DC-DC converter, it's a DC-DC converter that increases the input DC voltage into a higher output DC voltage. In this case, the input is 200, and we see that the output is oscillating around 350 volts. So it's a gain of something like 1.75. But you see that it's oscillating a lot around this output value, and we'll be able to change the behavior of the circuits, so this oscillation, by modifying the parameters. So we see now that the switching frequency of the IGBT is very low. It's around 50 hertz. So if we want to have something that is more DC for a load voltage, I propose we increase that switching frequency a little, let's say to 320 hertz. We already see that the range of the oscillation is much smaller. If I go, for example, to 1500 hertz, now it's roughly DC. You still see it oscillating, but be careful that the scale here is automatically adjusted. So now it's switching between 390 volts to 403 volts. If I want to change the output voltage level, I can play with the duty cycle. If I increase the duty cycle, normally the output voltage will increase. So now it's around 650 volts when the duty cycle is at 70%. If I put it down to 30%, it's around 298 volts. I can also play with the input DC. If I change the input DC voltage, you also see that the output, the load voltage changes. Now what I will do is that I will connect the external controllers. If I go back to my Project Explorer, I'll open the controller VI, and I'll deploy the controller program. So this controller works, as we can see here. There's the boost converter running on the Compact Rio, and on the Mario you see there is a PI controller that is tracking a reference that is set inside this VI here as the VLoad reference. So now we will be tracking 300 volts as soon as I go here and I connect the external controller. So now if you look at the webcam, what happens is that the Compact Rio sends as an analog output the load voltage that is read by the Mario, and the Mario sends the IGBT control as a digital output, and it enters as a digital input into the Compact Rio. So as you can see now, the load voltage is approximately 300 volts. If I show both panels at the same time, so the control and the converter panels, you can see that if I change the load voltage, for example, to 200, the duty cycle will be adjusted to track that reference voltage. So now the duty cycle is around 25%. And you see the DC is very good because I have a PWM frequency of 3 kilohertz. If I bring that down to something much smaller like 200, you will see the oscillation over and under the reference voltage. So that concludes our first demo. Just stop this one, stop this one. I'll go back to my presentation. Oh, we have we want to answer a question, I think. What is the question, please, Sabrina? The question is, do you think these teaching laboratory could be of any interest in your university? So I invite you to answer this poll in your GoToWebinar interface. Okay. We'll take a few seconds. Okay, thank you very much. If I go back to the presentation, so this is just to explain you again how this external controller was working. We have the load voltage as an analog output that was going from the Compact Rio to the Mario, and the switch control was going from the Mario to the Compact Rio through the digital signal. When you are doing such a closed loop simulation, something that is important is the loop time of the simulation. So in this case here, we see that the Compact Rio is running around 300 nanoseconds, 200 to 300 nanoseconds loop time. But then we have to take into account the delays of the analog output module and the digital input module of the Compact Rio, and also the equivalent delays inside the controller. So we can expect it to be approximately the same for the analog input and the digital output of the Mario. So in total, we could expect the loop time to be the sum of all these delays. So approximately 300 nanoseconds for the solver plus 8 micro for the analog output, 100 nanos for the digital input, and let's say times 2 to take into account the delays in the controller. So we are talking here about something like 20 microseconds. At this point, I'd like Ben Black to explain to you a bit more about the last 3 modules of the courseware. Ben?
Yeah, as we've talked about there, we divided the courseware into these 4 modules. The first one that we showed the example was the DC to DC converter. The second module is an AC to DC rectifier. So it'll go through the principles of a diode rectifier circuit and look at kind of all of the technical details of the analysis of that circuit. The exercises will allow the students to vary parameters that change the ripple and impact the smoothing of that circuit. So it walks through the theory and the application of that. So the circuit being analyzed is this you see on your screen here. This is a screenshot of that, or a block diagram of that circuit for the AC to DC rectifier. The third module is a DC to AC converter. It'll step through the principles and a 3-phase, 2-level inverter, and then the PWM techniques associated with that. This module also has a rapid control prototyping and a hardware in the loop component. So you'll be able to use the MyRio for the control side and the Compact Rio for the hardware in the loop simulation at the same time. The exercises allow the students to walk through the impact of the neutral point connection and filtering, varying the PWM frequency, the dead time, those sorts of things that actually go into implementing a real 3-phase inverter application. So they'll go through all of the different components that go into the design of that inverter. And you can see this is a screenshot of the front panel of that laboratory and also a block diagram of the inverter being simulated, the inverter and the load specifically. From the control side of it, there are 2 different control algorithms that the students will be exposed to and work with. The first will be just an open loop control example, so using a sine triangle PWM generation scheme in an open loop manner to generate 3-phase power. And then the second version of it is actually a closed loop control algorithm for 3-phase generation, where the students will be able to implement and tune and work with a full closed loop inverter control system. So the students will be using a hysteresis control algorithm for that, and then they'll kind of step through the different parameters within that hysteresis control to understand better the impact of the hysteresis band and the pulse modulation on the closed loop behavior of an inverter circuit. The fourth and kind of the pinnacle of the teaching laboratories that we've put together is a 3-phase neutral point clamp converter. And so this is definitely the most complicated of the exercises, the most complicated of the modules, and it takes the students through the design, the component sizing, and then the kind of the configuration of an NPC implementation. So here's the screenshot from the laboratory and also the circuit diagram that's been implemented in the HIL system. And so the kind of the point of this lab is to introduce the students to a higher complexity control, higher complexity circuit, and also kind of the higher complexity implementation of this type of algorithm. And so I think we're going to go back to Pierre-Yves to show us kind of exactly how the students will go through this laboratory.
Okay, thank you, Ben. So what I'd like to do for this exercise is actually I'll go back to my LabVIEW project explorer, and I'd like to go to the PDF of the module and actually make one of the exercises. So here's the PDF. Now I'm well prepared, so I know that the exercise I want to do is at page 32. So I'll go to page 32. maybe it's not. So the exercises I want to do is at page 29 actually. So I will take the NPC, the neutral point clamp converter, and what I'll do is that I'll vary the input DC voltage and look at the behavior of the currents of the three arms. So now the load here is not a normal RL load, it's an RLE load. So there's a back EMF, and we'll see the effect of it. So to do it, I'll go back to my VI here. I will select the three-phase, three-level NPC converter, and I'll deploy the simulation. So now I won't put this in full range for now because I want to look at the exercise at the same time. So what the exercises ask, so it will ask me to change the DC voltage source to different values and observe the level, the 5 levels of the branch-to-branch voltage, depending on these 5 levels. So it asks me first to put it at 150 volts. So I go here and I select 150 volts. These 5 levels, if I look here, I will have 150 volts, 75, 0, minus 75, and minus 150 volts. So the student will go here and just write these 5 values here. And then I go here, and the exercise says to put 120, so I move this to 120. I see there was not much difference, but as I said, the scale here was readjusted automatically. So you see now it's 120 for the first level. Second one is 60, 0, minus 60, minus 20. So it really looks like the 5 levels will be just VDC, VDC over 2, 0, minus VDC over 2, and minus VDC. So just to confirm, I'll do the last 2 values, so 90 and 80. 90 should be 90, 45, 0, minus 45, minus 90. It works. And finally 80. So I have 80, 40, 0, minus 40, minus 80. That's perfect. This NPC converter is working perfectly. Next question is, any comment when U equals 80 volts? It looks like it's working. What's about this current? The current is very noisy. Actually, it's not that noisy. If we go back to 150, you'll see that the current here has a range of minus 30 amperes to plus 30 amperes. But when I'm at 80, it's between minus 3 and plus 3 amperes. So what could have happened here? The exercise says to look at these bottom two scopes. So what I see here is the green line, which is the back EMF of that phase, is really overlapping with the branch-to-branch voltage. So I think we have this very small current because we are in inverter mode, but very near the point where the NPC converter will actually be in generation mode. So the back EMF will give power. So I think that's really what's happening here. I'm not an expert in power electronics, but I think the students will have more hints for this. I'll go back to the presentation. So that concludes the demos for today. I'll just stop this one and go back to my presentation. So now that we've shown you the demos, I'll explain a bit more what is the electrical hardware solver, or EHS solver. That is the FPGA-based solver used for all these demos. So it's an FPGA-based solver, so it's running in the zinc chip of the Compact Rio. We use FPGA-based solver so that we can have a very fast, a very short loop time. in order to be able to handle very fast switching frequencies. So this is why we are using the EHS solver. Actually, it's an amazing tool because it's very easy to use. The idea is that the circuit is designed with a generic circuit editor, so for example, SimPower System, PSIM, Plex, and the actual matrices that are solved for the simulation are automatically generated and loaded onto the FPGA at the start of the simulation. So you don't need to know any VHDL, you don't need to have any FPGA expertise to use it. It's really easy, and you can use it out of the box. These are a few examples of the sample times that we can achieve with the EHS solver. So in general, that sample time will be between 125 and 500 nanoseconds. For the DC-DC converters that we have, it's really the sample time is depending on the complexity of the circuit and also the number of scenarios that we want to be implemented in the circuit. So for the DC-DC converters, the boost converter I showed you, or a buck converter, buck boost converter, they are all at 200 nanoseconds. For the others, they are depending on the complexity, they have a longer loop time. And the most complex circuit that we've shown you today was the NPC converter, and this one is running at a loop rate of 2.7 megahertz. So that means a sample time of 368. So as I said, it's a generic solver, so you can create new exercises. So the teaching laboratory comes with the set of exercises that were presented to you by us today, but you can actually generate new exercises. We support a large subset of the libraries of the tools we support. We're talking here about passive components, inductors, capacitors, resistors, also transformers, switching elements, so a diode, which is naturally switching, or an IGBT, ideal switch, or a breaker, for example. So up to a very large circuit. And depending on the circuit you want to implement, so the new exercise you want to make, you may want to modify the LabVIEW panel and the LabVIEW model in order to include new scenarios, so PWM generators, signal generators. So this can be done through the LabVIEW interface. And now the thing you are waiting for is, how do I find this package? It's very easy. You go to the VI package manager tool, and you can download it directly. You'll see within the package what's important. So just to explain to you how to do it, as I said, it's very easy. You go to the VI package manager. It is loading right now. And here, if you just write down OPAL-RT or power electronic software, you will find that power electronic software tool. Here it's already installed, but you can get infos. So here it's already installed, so if you click Show Examples, you will also see the project I used before. So it's really that easy to install. You just select here and you install it. As I said, Show Example will bring you to the installation folder of the package once it's installed. So now I will pass back the presentation to Pierre-François, who will give you the conclusion of the webinar and also maybe talk you about the special of the day.
Thank you very much, Pierre-Yves. So in conclusion, what you've seen is that learning power electronics bases using HIL and RCP. Hold on a sec, excuse me. It's commonly used in the innovative power electronic industry. So what we want is to give the look and feel of HIL and RCP through power electronics to university when students are learning power electronics. So as I mentioned, the teaching laboratory is available with 2 hardware platforms, available with National Instrument Compact Rio and OPAL-RT. And I will give you further detail about the configuration needed for the OPAL-RT system. So right now it includes 4 courseware made by experienced power electronic teachers. And as you could see, there's a cost advantage versus real analog power electronics laboratories that we usually see right now all around the world. And when I want to talk about cost advantage, one of the main purpose of our collaboration with National Instrument is really to have a level entry laboratory which is very, very, very low cost. And as you will see on the next slide, you could directly buy those teaching kit online, either through the NI website or either to the OPAL-RT website. And one of the main things is that through the NI website, I think it will be very important to log in yourself as academic user. When you will log yourself through academic, you will have a special price just for academic. And when you want to equip yourself with the Compact Rio, with the courseware, as well as with the My Rio, the cost is lower than $2,000 US dollars. So it's a very good pricing. And in terms of OPAL-RT, when you click on this, for sure you could buy the OP45000, you could buy also the OP4668, and you will see that some of us know some of our features is that we provide the platform that you could easily upgrade with other softwares to use any other of our development software, which are a bit costly for sure, not a bit costly, but more provide you more cost, more. But for sure, we start with a good pricing, and because we know that a lot of you are already using the OP5600 as well as the OP4500 family, we'll let you know that this courseware is compatible with the a lot of people are laughing here, so it's very difficult to concentrate. But what we want to offer you today is for the first 3 users who buy this courseware online, we'll give you a 50% discount. At OPAL-RT, we made a lot of effort to develop our online buying process, and we'll be more than happy to provide to already existing OPAL-RT users the chance to use the courseware with their already existing system. We have another poll question that we would like to send. So what we would like to know basically is, I will launch it in a few minutes. Yeah, so you could launch it. Yeah. So, oh my God, yes. So, okay. So I think first of all, we would like to see which teaching module you would like to see. I think there are some problem with the configuration of the pool, but if you could send your ideas through the chat, that will be very appreciated. We really would like to know and understand if we continue to develop more complex or wider power electronic experiment. So your feedback here is very important. Okay, I would like to finish by saying that in now 2 weeks from now, we will hold our OPAL-RT user group in California. It's going to be the May 13 and May 14, 2015. This technical seminar is free. We will cover a lot of topics, and of course, one of our partners will be National Instruments, who will be there. And together you will have more hands-on on this power electronic teaching laboratory. And also, it's not the end of our venture with the National Instrument. We're already working on the on other products and other offer we could jointly do together. And I will let the end note to Ben if he wants to add something. Thank you very much.
Yeah, thank you, Pierre-François. We're very excited about the launch of this academic tool, but as Pierre-François said, this is just kind of the beginning of our collaboration together. We'll be presenting this tool at the RT15 conferences, not just in Berkeley, but at some of the other ones around the world. We'll also be talking about the potential of tying some of National Instruments' grid-deployed hardware, like our new phaser measurement unit, the grid automation system from National Instruments. We'll be talking about how to tie those sorts of deployed hardware targets into something like ePhaser Sim, tying it into a large wide area network simulation. And we're excited about this collaboration. We're excited about what it brings to the market, and we're excited about kind of where we're going together as two companies. So we look forward to hearing feedback about the teaching tools. We're really interested in getting direct feedback from you as end users about how the tools look and feel and what you would like to see added onto the tools. We're excited about being able to open up the solver for you as an educator to expand and build upon the pieces that we've pre-compiled for you, because I think that's really where a lot of value in this lies, is the ability to extend it and to add and build on top of it. With that, I would like to thank you all for joining us today, and we hope to hear from you about this collaboration.
Okay, thank you. Thank you very much, Ben. We will have the time for approximately 10 minutes of questions, so I invite you to give more questions if you can. After the question period is finished, if we don't have the time to answer all questions, we will answer you directly via emails. Also here with us we have Mr. Youssef Bedustani, which is one of our FPGA-based solver experts here at OPAL-RT, to answer your questions, if you have any for him. So Sabrina, which question do you want to do first? So first question is, we have a MATLAB and OPAL-RT in our college. Which one is better, MATLAB plus OPAL-RT or NI plus OPAL-RT? I think for the EHS solver is the same solver implemented on both systems. So I would really say that it depends on your preference on the environment. Development environment. Next question is, how does EHS deals with the numerical oscillation in the process of the model? So this one. Youssef, do you want to answer? We have Jean Bélanger here, our CTO, who maybe wants to answer. So Jean, how does EHS deal with the numerical oscillations in the solution process of the model in EHS?
Yes, first I would like to thank this experienced user. I think the problems of the periodic solver is quite well known. So you will see that in the next generation that we will have in a few weeks, that we succeed to improve the solver to eliminate this oscillation and eliminate the losses. For this student version, we simply eliminate the oscillation by taking the average over about 20 microseconds.
Okay. Next question is, I mentioned that we can use SimPower System to build the model. Yes, it's at OPAL-RT it's our preferred tools, but we also support Plex, PSIM, and Multisim. And the next question that goes with it is, can you then use MATLAB SimPower System to implement a power electronic converter on the Zinc? Yeah, the SimPower System toolbox is a Simulink toolbox, so that's our main way to design circuits. So really the SimPower System toolbox is really used just as a design tool for the circuit, and then OPAL-RT EHS will deal with the rest of that, of the simulation process. Next question. Is it possible to have an explanation about the DC-DC converter buck boost with LabVIEW and how to run it? It's more or less the same idea as the boost converter. So it's one of the exercises. Maybe I can go back to my simulation here. I was using the boost, and there is also the buck and the buck boost. So it's the same process. You just deploy the simulation with this button here. It's really the same process. Do I have another question? Oh. I have a question here that says, is there a possibility of having a large-scale version of this service for an entire course remotely? For instance, many courses are now moving to distance section where students are primarily working from home. Could they remotely access this lab and complete simulations in this way? Technically, there is no real limitation in this, because in this simulation here, we access the simulator through the Ethernet access. So basically, if you can connect to a VPN and have access to that IP address, there is no really technical limitation in accessing it. Okay. Okay, I have a question here that says, can you please suggest implementation or can we design controller to control microgrid in MATLAB and OPAL-RT? So I'll let Jean Bélanger answer this.
Yes, of course, this is designed for that. I mean, these teaching tools are, I mean, they have all the capability and power to design a real power system. Now, if you would like to design a microgrid, and if the microgrid is very large, then you will need to use our advanced package with the simulation of maybe of a distribution system with more than 400 or 500 nodes. But if you want to simulate a very small one, then you can use this educational package. But you can extend the same principle to any type of controls and multi-drive system. So it all depends on the capability of the hardware platform. Yeah. Does and does NI AHS run larger scale EC system simulation? So what we have implemented in the actual NI hardware at that price is the entry level. So we have much larger capability, but then you need a larger FPGAs. So it's nearly based on what is the size of the platform. So we have customers that will use 5 or 10 FPGAs all connected together. But the aim of this first product is mainly for the undergraduate market. So yes, but it depends on the platform.
teaching bundle a motor component for real signal measurement?
Okay, this is as a motor component. Okay, that's does this teaching bundle have a motor component for real signal measurement? Motor component. I mean, this is the objective of the next series of tutorial tool that we would like maybe to make tools for that will be concentrate on motor, on different type of motor teaching with the different type of inverter and different type of inverter and motor. So we plan to do many of these teaching material, and in fact we request help from good teacher. If they are some good teacher would like to help us to prepare this material, you are quite welcome.
About power factor correction circuit using boost converter.
Yeah, but this is a standard. As long as you can implement your about power factor correction circuit using boost converter. I mean, if you are able to implement your control system, you are able to do whatever you want. Here there is no limit. We use a real controller connected to a virtual plant model, so there is no limit on the plant model that we provide except the size. So if you need a bigger size, then we need to provide a bigger hardware. But all the basic teaching or principle could be demonstrated. IDT, can you?
So we have another question here. It says, can you run a boost converter with a high duty ratio? In cases of high duty ratio, I mean, there is no limitation in duty cycle ratio itself, but you are limited with the solver sampling time. So as long as if you resample your control signal at, for example, 300 nanoseconds, and you still have signal, then if you're happy with the resolution of that duty cycle, then the simulation will be correct. Or also the I/O interface. If you're interfacing with an external controller, then you are limited by the resolution or the precision of your digital inputs. But for lower switching frequencies, that should not pose problem. Next question. I have a question here. Can this software be used for studying grid-integrated power electronic devices? I'll let Jean answer this one.
Yes, there is no limit to the software. Is that right now what we put in this package is the entry level. So if you want to simulate large power grid, large transmission system with many machines, then we need to go to the more complete package. But this is what we intend to do, is try to make some educational package for this type of application. But in this case, if the grid is very large, we can simulate it at 50 microseconds, so we can use the simple processor platform.
Okay, thank you. Our time is up, unfortunately. For the other questions, we'll contact the people who ask the questions directly via email, probably. And the PowerPoint of the simulation will be available on our website and also on the NI website shortly. So I invite you to go there. Thank you very much for attending, and have a good day.